Okay, the last intermolecular force that we're going to discuss is London dispersion forces. Now, so far, all the three intermolecular forces that we've discussed so far have involved polar compounds. Now, so of course, we have to talk about how nonpolar molecules interact with each other and any attractive force that they may have. Okay, so this occurs in all, this force occurs in all molecules, but it is the primary or only force for nonpolar compounds. Okay, and so to take a look at how London dispersion forces, primarily people just would refer these as dispersion forces. Let's take a look at a helium atom. Now, a helium atom is sort of a simple example here, but it's certainly nonpolar. There's no bond there, so there's not going to be any excess distribution of electrons. We know that its 1s2 electrons will be randomly distributed through its 1s2 orbital. So at t sub 0, so initial time, those electrons are flying around, and at that point in time, they're, say, in that distribution. At some point in time later, let's say t1, the electrons might be somewhere else. Okay? And even later, let's say T2, they might be in a different place. And it just so happens that at one point in time, just because of sheer probability, the two electrons could be localized in one area. So we could say at the top of this molecule. Okay? Just for a second, and again, this only happens because of the random probability predicts that at some point in time they're going to be near each other. Now, it certainly doesn't happen to occur often, but probability tells us that it will happen at some point in time. And then again, sometimes later, let's say T3, those electrons are randomly distributed again. But at T2, something very significant occurred. Because the electrons, because of sheer probability, were localized at one area, what that set up is a dipole moment, where we have a local excess of electrons, and then an absence of electrons to shield the nucleus over here, so there's going to be a partial positive charge. Okay? That is known as an instantaneous dipole moment. Okay, it only happens for an instant, but it does happen, and there is a partial negative charge and a partial positive charge, a dipole moment. And a microsecond, a nanosecond later, those electrons are randomly oriented again. Okay, but they do happen. Okay, now what would happen if another helium atom, let's call this helium atom A, and this is helium atom B, what would happen if a neighboring helium atom was just close enough to the helium atom A, which underwent a instantaneous dipole moment? Of course, that partial positive charge on the helium atom A would attract electrons from helium B to one end of the atom. Okay, what's that going to do? It's going to set up a partial negative charge here and a partial positive charge at the other end. And what this is, that is an induced dipole moment. The helium A had a dipole moment just because of sheer random probability, an instantaneous dipole moment, but because helium B was nearby, its dipole moment was caused or induced by helium atom A. Okay, so now we can see where nonpolar molecules can, or how nonpolar molecules can be attracted to each other. When these instantaneous or induced dipole moments set up, there are electrostatic attractions between them, between the partial positive charges and partial negative charge. They are certainly weak because they only happen randomly and for an instant, so this is our fourth strongest intermolecular force. Okay. All right, but these can start to build up for molecules. There are some nonpolar molecules that are liquids at room temperature. There are even nonpolar molecules that are solids at room temperature. And dispersion forces can start to gain sort of traction or start to build up for a couple of reasons. If the molecule has a large surface area, if the molecule has a large area for interaction, a large surface area, the interactions, the dipole moment, the partial negative charges can build up, and some to be in a very strong attractive force. Molecules with small surface areas have little interaction, and their partial negative and partial positive charges don't sum up very well, so they have lower intermolecular forces. So as we'll see, intermolecular forces will, as we previously saw and as we'll talk about again, intermolecular forces dictate boiling point. N-pentane, a straight chain hydrocarbon, looks like a seesaw function because of all the tetrahedral geometries, has a higher boiling point than the boiling point for neopentane, an isomer of pentane, because of the lower surface area of neopentane. So the larger the molecule is, the more surface area, the higher the intermolecular forces due to dispersion forces. The second way that intermolecular dispersion forces can start to build up is polarizability, or how strong of a dipole moment can an atom molecule create. For instantaneous or dipole moment. And it happens to be the higher the number of electrons, the more polarizable. Okay, and number of electrons increases with number of mass. So if you look at a molecule, the molecule with the higher molecular weight is more polarizable. And the higher the polarizable, more polarizable the molecule is, the greater the dispersion forces can be. So a molecule like CCl4, carbon tetrachloride, we take a look at it. We've taken a look at that molecule. It is nonpolar, but it's got 4 pretty big chlorine atoms that have a lot of electrons. It's very polarizable. Carbon tetrachloride is a liquid at room temperature, whereas something like methane, CH4, is a gas at room temperature because carbon tetrachloride's dispersion forces increase because it's more polarizable. Okay, so here's a summary of the 4 intermolecular forces we've discussed so far. And as we showed, the strength increases. Ion dipole are strongest intermolecular forces, again, because we've got that full positive charge. Remember that the interactions between the ion and the polar molecules can overcome full positive, full negative interactions because there's multiple waters of solvation. Okay, when hydrogen is bonded to a very electronegative atom, it creates a very strong partial positive charge, and that is a very specific case of dipole-dipole interactions, stronger. And so we call it something completely separate. Again, dipole-dipole interactions is that same interactions for just your normal run-of-the-mill polar molecules. And again, the weakest are dispersion forces. They occur in all molecules and atoms, primary mechanism for nonpolar molecules, and they occur when just by sheer chance electrons are at one end of the atom or molecule, sets up an instantaneous dipole moment, which can induce a dipole moment on a neighboring molecule, and of course that attraction is our dispersion force. Okay. So now let's take a look at some of the impact of hydrogen bonding. Okay, so now we know, if we take a look at group 6A and group 4A molecules, we know that as the molar mass increases, intermolecular forces will increase, dispersion forces, so boiling point should go up. And for group 4A, that is absolutely true. As the molecular mass comes up, the boiling point also comes up. We can take a look at it the other way. As the molar mass goes down, the boiling point goes down. If we take a look at group 6A, that trend stays true. Tellurium, the biggest atom pictured here, the most polarizable, it has a higher boiling point than selenium. Selenium is bigger than sulfur, so it has a higher boiling point than the sulfur hydride, as we're seeing this. But then water, because it hydrogen bonds, has an immensely greater intermolecular force connection to its neighboring molecules and raises its boiling point to 100 degrees Celsius. If they didn't hydrogen bond and we sort of took this trend through, water would not be a liquid at room temperature. It would have a boiling point around negative 100. So liquid water wouldn't be present here on Earth. And if liquid water isn't present here on Earth, life as we know it would not have evolved as, of course, we know it. Okay. Another set of molecules where this becomes very important is the nucleotide bases for DNA. You probably know that the 4 base pairs, or the 4 molecules that form the base pairs, link together in a specific ratio to make the double helix of DNA. Thymine nucleotides connect with adenine, TA as they're often called, or AT, and cytosine connects with guanine. And the reason why they do so in that sequence is because thymine and adenine have 2 connections for hydrogen bonding. Cytosine and guanine have 3, and so that's why they link up in that specific sequence. Okay, when your cells want to make new DNA sequences, or when forensic chemists want to replicate DNA for PCRs, through PCRs for DNA profiling, what you want to do is you want to take a small amount of DNA and make more of it. And the way our body does it, and the way we can do it chemically with PCR reactions, is by taking apart the double helix. Your body does it through an enzyme, copying the strand of each strand of DNA. And so now when you've got 1 DNA molecule, you can make 2 by removing or breaking that hydrogen bonding and then repairing it with a new set of nucleotides. Okay? It turns out that if London dispersion forces is what held the nucleotides together, the interactions would be too weak in aqueous solutions and we wouldn't have a double helix. Same thing for dipole-dipole interactions. They're just too weak to hold the DNA in a double helix conformation in aqueous solutions. If they would have been kept together by covalent bond, that would be too strong for enzymes to sort of peel off the 2 strands of DNA. It just so happens that hydrogen bonding is just right, and that's what keeps this mechanism working.